Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course. States of matter. Today we begin with lecture 15 from the course, but make sure you watch the previous ones before viewing this one. In the last lecture, we saw a few problems based on the Avogadro's law, so I hope the concept now is clear to you. In case you still have any doubt, please feel free, put your doubts in the comment section. Email them to us. Email ID of ours is always written on the last slide of each lecture. Also, you can join us on the Facebook page of the channel, and the Facebook page has the name as H2O Chemistry. That is the same name as that of the channel itself. Now, you have learned all the four gas laws with the last lecture. That is the Boyle's law, the Charles law, the Gay-Lussac law, as well as the Avogadro's law. And in all these four laws, what you have seen is that we have four measurable properties of the gases, that is temperature, pressure, volume, and the amount of the gas, which we are going to always take as the number of moles of the gas when we see a relationship between these four. Right? And what we have learned is that in all these four laws, we keep two of these constant and we see a relationship between other two. Now, the problem is that it is not going to be always that only two of the properties they are going to change with respect to each other. It is also a possibility that in one state moving on to the other state of the gas, there is a change in three properties or four properties. So how do we understand those problems or those daily life situations where these things are going to happen when there is going to be three or four of these variables changing? For example, if I give you that we have a balloon, right, and in this balloon I have filled in some air. Okay, so this means that the amount of the gas, I can say this is going to be constant because I have filled in some air and tied this balloon, and now I release this balloon into the air, right, and the balloon starts going up. And this is something that you have been enjoying it probably when you were very small, see, releasing the balloon into the air and just keep on looking at it, enjoying it move higher and higher till this becomes out of your sight. Right, now what is happening to this balloon when it is going up is something that we should understand. Well, when the height is going to increase, supposedly this is sea level and this is some higher height till what you can see the balloon going up. So as the balloon is going to rise higher, what we know is that the density of air is going to be maximum at this point. And as we are going to move to a higher level, the density is going to decrease, right? Because the air is getting thinner. And you've also learned that air is getting thinner, the atmospheric pressure is also going to decrease, right? So the pressure is going to decrease as the density is going to decrease. Now from the Boyle's law, what you have learned is that pressure, this is going to be inversely proportional to volume. Right, so this means that with decrease in pressure, the volume of the balloon is going to increase, right? And supposedly if the temperature is constant, so this is going to be an increase in the size of the balloon. Now the other thing that is happening when the balloon is rising up is that with increase in altitude, the temperature also decreases, right? So as the temperature decreases, you can, I hope, correlate that to the Charles law, the temperature is directly proportional to the volume. So if temperature is decreasing, the volume should decrease. So this should decrease this way, right? So one thing is the pressure is causing the volume to increase, the temperature is causing the volume to decrease. So it is going to be a net effect of both these, the pressure and the temperature, on the volume of the gas. This is going to cause the change in the size of the balloon. So what we mean for this is that there we are seeing that the amount of the gas is fixed, but the pressure, the temperature, the volume, they are all changing for the balloon constantly. So we should have something with us which can give us an understanding that what is going to be the final state and the initial state of these three variables. And for this, what we have is the combined gas law or the ideal gas equation. right? So I hope you can now understand why we need to combine all these gas laws and how we are going to get after combining all these gas laws, the ideal gas equation where we can see a relationship of all these four measurable properties when they are all changing with respect to one another. Fine. So I hope now you have an understanding why we should learn this first of all. So having understood this, let us learn what is the combined gas law and the ideal gas equation. So the combined gas law, also known as the ideal gas equation or the equation of state, states that for a given mass of a gas, the product of its pressure and volume divided by its Kelvin temperature is a constant. So what do we mean by this is that the product of pressure and volume PV divided by the temperature on the Kelvin scale or the absolute temperature, this is going to be constant. This is what the gas law says, the combined gas law that says to us, right? So I'll be just removing this so that you can see the rest of the things also. Now, this combined gas law, this is going to therefore give us the simultaneous effect of the changes of pressure, temperature on the volume of the gas. So what you can see is that supposedly we have an initial state of the gas where the pressure is P1, the volume is V1 and the temperature is T1. And from this, what we see is that we are changing all these three and we are reaching up to a final state where the pressure is going to be P2, V2 and T2. And what we want to learn is what is the relationship of these two. Fine. Now what we can do here is experimentally that what we can just break this change into two steps. Okay, you can just assume this that this is happening in two steps, and the first step is when we are going to keep the temperature constant, and keeping the temperature constant means that T1 is going to remain T1. The pressure changes, let us suppose, from P1 to P2 and the volume changes from V1 to V. And in the next step, what we will be doing is we will keep the pressure constant, and keeping the pressure constant, this means P2 is going to remain P2. The volume is going to change with change in temperature. That is going to be V changing to V2 and T1 changing to T2. And with this, we have achieved the final state that we wanted. So let us understand what is happening one by one. So this is the diagram that we just now saw. So here, first step, we will be applying the Boyle's law, because what we have is that the temperature is constant, and this we are assuming that this we have taken a fixed amount of gas. Okay, so fixed amount of gas, temperature is constant. This means that we can comfortably apply the Boyle's law, and what we will be getting is P1 V1 equal to P2 V. Right, so this is what we have from the Boyle's law. What we can write as the volume, this volume over here, that is after the first step, V is going to be equal to P1 V1 over P2. Now to the second step, we are going to apply the Charles law, because here the pressure is constant. And when the pressure is constant for a fixed amount of gas, we apply the Charles law. So the Charles law says that the volume is directly proportional to temperature. So we have V over T1 equal to V2 over T2. So this is the initial volume and temperature, and this is the final volume and temperature, right? Now over here, for this value of volume, we are going to replace it with P1 V1 over P2. And what we will be getting is P1 V1 over P2 T1 equal to V2 over T2. And just rearranging it, what we will be getting is P1 V1 over T1 equal to P2 V2 over T2. And what does this mean? This means that PV by T is going to be constant. Let us say this is equal to a proportionality K. And now this is not K1, K2, K3, K4. We are just calling it K because we are combining all the gas laws now. Fine. So what we get from this is that PV equal to KT, and just remember this equation as equation number 3, because I'm going to continue further on to the next slide with this equation that we have obtained. So now for any given value of pressure and temperature, that means if you are going to keep the pressure and temperature of the gas constant, the equation 3 that you saw just now, PV equal to KT, from this we are going to get that K is going to be directly proportional to the volume of the gas. Now, one thing more that you have learned while you were learning the Avogadro's law was that when the pressure and temperature, they are constant, the volume of the gas, this is directly proportional to the number of moles of the gas. So from this we can also write that K is going to be directly proportional to the number of moles of the gas. And if we remove the proportionality constant, what we can write this as is that K is equal to NR, where R is now going to be the gas constant per mole. And this R is called as the universal gas constant because you can use this for any gas. Okay, so the value of this R, the gas constant, is going to remain the same. So replacing the value of K equal to NR in the equation PV equal to KT, what we will be getting is PV equal to nRT, and this equation is called as the gas equation or the ideal gas equation because it is the ideal gases which are going to follow this equation because they are the ones which are going to follow these gas laws. As far as the real gases are concerned, which you will be studying a bit later on, you will be seeing that they do deviate from the ideal gas behavior. What conditions that is going to happen, that is also going to be learned slow and steadily in this as the course progresses. But this equation PV equal to nRT, this is called as the ideal gas equation, and very importantly, R is known as the universal gas constant. So now that you have learned how experimentally we reach up to the ideal gas equation, the ideal gas equation can be derived very simply by just combining the three gas laws, that is the Boyle's law, the Charles law and the Avogadro's law. So let us quickly see that also because that is very easy for you people to understand. So the Boyle's law says that the volume is going to be inversely proportional to the pressure of the gas at constant N and T. The Charles law says that volume is going to be directly proportional to temperature at constant N and P, and the volume is going to be directly proportional to N at constant T and P. Now, if you see all these three equations, we have volume in common for all the three equations. So we'll just club these together, and what we will be getting is that V is going to be directly proportional to NT by P. Fine. And if we remove the proportionality constant, what we will be getting is that PV equal to nRT. The proportionality constant has been replaced by the gas constant R. Right? So PV equal to nRT, this is the ideal gas equation which we can achieve by combining these three laws. Why we have not used the Gay-Lussac law over here is because that does not give us a direct relationship of the volume. Fine. So all these three equations, they just give us one common thing, that volume is related to pressure, temperature and the number of moles of the gas. Perfectly fine, I think. Now very easy to understand as well. Now what we infer from this is that we have a relationship between pressure, volume and temperature as it is occurring in two different processes also, right? So while you were seeing the experiment that we had a final state, the initial state P1, V1 and T1 reaching up to the final state P2, V2, T2, and we now have a relationship between pressure, volume and temperature. How? We have the relation P1 V1 by T1 equal to P2 V2 by T2 when we have a fixed amount of gas, right? So if N is going to be constant, R is a constant, PV is going to be directly proportional to T, or you can say that PV by T is going to be constant, or you can say that P1 V1 by T1, this is going to be equal to P2 V2 by T2. Fine. And this is how you are going to use these three, uh, the relationship between the pressure, volume and temperature for any amount of gas in your numericals also. Fine. Now let us learn the nature of the universal gas constant R, because this is going to be very important for your understanding. What we know is that PV equal to nRT. So this we can write as R equal to PV by NT. Now P is pressure, V is volume, N is the number of moles of the gas, and T is going to be the absolute temperature. So pressure we can also write as force upon area. So this is going to be force upon area into volume over number of moles into absolute temperature, right? And also we know that area is going to be equal to length square and volume is going to be equal to length cube. So this length square is going to cancel from both of these. What we will be getting is that force into length divided by number of moles into absolute temperature is going to be R. Now force into length, what you have learned in physics, is going to be work, right? So work upon number of moles of the gas into absolute temperature, this is going to be equal to R. So what we can say is that R is going to be the work done per degree per mole of a gas. Now, the next thing that we have to learn over here is what is going to be the numerical value of this universal gas constant, because this value is going to remain the same for any gas. So let us learn how we are going to find out this numerical value of the gas constant R as well. So finding out the numerical value of R, what do you require? Well, we know that PV equal to nRT, or R is going to be equal to P into V by N into T. So if you have any set of values for pressure, volume, the number of moles of the gas and the temperature, we can find out the value of R. And there is one set of values that is already what you have learned previously while we were doing the Avogadro's law. There I told you something about STP. Right, what we learned is that at STP, that is standard temperature and pressure, the volume of 1 mole of a gas, that is 1 molar volume, is going to be equal to 22.4 liters. Right, I hope you remember. So putting that information over here, what we have is that at STP the pressure is going to be 1 atmosphere, the temperature is going to be 273 Kelvin. We have 1 mole of a gas occupying a volume of 22.4 liters. So we will be putting all these values into this equation and getting the value of R to be equal to 0.0821 liter atmosphere per degree per mole. Now the other thing that you learned is that at STP, if the pressure is not 1 atmosphere but that is 1 bar, so the molar volume is going to be not equal to 22.4 but that would be 22.7 liters. So let us put that information also now. So we will be having, instead of 1 atmosphere, the pressure of 1 bar. So that at this pressure, 1 mole of a gas is going to occupy a volume of 22.7 liters. So we will be solving this to get the value of R to be 0.083 liter bar per Kelvin per mole. Also, what you can just now do is that you can keep on changing the units of pressure and the volume to get various values of R. Why we can do that is because as far as the temperature is concerned, it has to remain a absolute temperature, right? So you cannot change it into degrees Celsius or Fahrenheit. You have to keep it the same absolute temperature. So N, the amount of the gas, also you have to take number of moles of the gas only, there can be no change. But for pressure and volume, we can keep on changing the units to get various values for R as well. So now if, for example, if we convert liters into ml, right? Well, we will be doing this for this equation. Okay, so we have liters being converted into ml, atmosphere remains atmosphere, and it is going to be Kelvin and mole. Okay, so what are we going to do? Well, we have just converted liters into ml, so this means that we will be multiplying this by 1000, and what we will be getting, the value is going to be 82.1 ml atmosphere per Kelvin per mole. So you can just keep on wearing them. I will be showing you a few more so that you have a thorough understanding and you are going to use these values in your numerical, so they are going to be very important. You can write this as 62.3 liters of mercury per Kelvin per mole. And here what have we done? We have converted atmosphere into So what have we done? We will be having the relationship of atmosphere and mercury as 1 atmosphere be equal to 760 So this value over here of 0.0821, just multiply this by 760. What you will be getting, the value is 62.3 liter per Kelvin per mole. Now let us quickly see some more values of R varying the units of pressure and volume. Okay, so let us quickly see when we have the pressure and volume in the SI units. So pressure is going to be in pascals or Newton per meter square and volume in meter cube. So what we have is that for 1 mole of a gas at STP, the pressure which is equal to 1 bar, we can write this as 1 into 10 power 5 pascals or 1 into 10 power 5 Newton per meter square. The volume is going to be 22.7 liter at 1 bar. So this is going to be equal to 22.7 into 10 power minus 3 meter cube, because 1 liter is equal to 10 power minus 3 meter cube. So temperature is going to be 273 Kelvin because we have it at STP. So putting these values, the value of R that you will be getting is going to be equal to 8.314 Newton meter per Kelvin per mole, or 8.314 Pascal meter cube per Kelvin per mole. And this is one value that we are going to use very frequently when we are talking about the energy changes that are taking place. Also, we can write this as 8.314 kilopascals decimeter cube per Kelvin per mole. So all your conversion formulas are going to be used over here that we learned while we were talking about pressure and volume in the lecture on the measurable properties of the gases. So now 1 Newton meter is equal to 1 joule. So we can replace this over here and get the value as 8.314 joule per Kelvin per mole, and 1 joule is equal to 10 to the power 7 erg. Okay, and that is in the when we are taking the pressure in dyne per centimeter cube and volume in centimeter cube, that we get the value of work as erg. So it is going to be 8.314 into 10 power 7 erg per Kelvin per mole. Also we know that 4.184 into 10 power 7 erg is 1 calorie, or 4.8184 joules is going to be equal to 1 calorie. So what we can do is divide this number by this value to get the value of the gas constant as 1.987 calorie per Kelvin per mole. Okay, and approximately we take this as 2 calorie per Kelvin per mole. Now if you remember these values, one value is that is of 0.0821 atmosphere liter per Kelvin per mole, one this value, and one this value as far as the calorie value is concerned. These three values, they are going to be very important, which will really help you in your numericals to do the questions very quickly. So this is just a quick chart for you people for the various values of the universal gas constant R in the various units, so that you remember them very well. Okay, so try remembering them, or if you do not remember them, at least you should have an understanding how we have attained these different values using different values for the units for pressure and volume. So now before I conclude this lecture, this is going to be the last slide, and before I finish up, I just wanted you to keep in mind the standard temperature and pressure conditions, because these are going to be very important for your numericals. So we know that the volume occupied by a given mass of gas, this is going to vary with the temperature and pressure. So we use STP or NTP, that is normal temperature and pressure, to standardize the values. Okay, and the standard temperature you know now is that 273.15 Kelvin or 0 degrees Celsius, that is the freezing point of water or the melting point of ice. And standard pressure is going to be 1 atmosphere or 760 that is what you will be generally using for your questions. And the volume occupied by any gas that is going to be 1 mole of a gas under STP is going to be 22.4 liters, which we call as the standard molar volume. And if we take the molar volume at 0 degrees Celsius under a pressure of 1 bar, this volume is going to change into 22.7 liters, right? So this is something that you will remember, always very important. Now, before we finish it off, last thing that we learned today is going to be the density of an ideal gas. Now, what is density? Density is mass upon unit volume. So what we know is that if we are going to increase the volume of a given mass of gas, okay, so mass we are making this constant and volume we are increasing. So this means that mass per unit volume is going to decrease proportionally. So what we have is that density, which is mass upon volume, is going to be inversely proportional to volume. So what we can write this as is equal to d1 by d2 equal to v2 by v1, or we can say that d2 is going to be equal to d1 into v1 by v2. Now another thing that we know for v1 v2 is going to be that p1 v1 over t1 equal to p2 v2 over t2. So what you can do is find out the value of v1 by v2 to be equal to t1 by t2 into p2 by p1. So we will be replacing this in this equation to get the relationship of the densities of the gases at two temperature and pressure conditions as well. So this is going to be another one thing that is going to be important for your numericals. So that would be all for this lecture. I hope you have understood everything thoroughly, because this is going to be one very important thing that you are going to use very frequently for all your questions related to the ideal gas equation and the maximum numericals related to this topic, the states of matter as well. So in the next lecture, I will be even discussing a few problems based on the ideal gas equation with you. In case you have any doubt as far as this lecture is concerned or any other topic of yours, please feel free put the doubt into the comment section. Email them to us. The email ID is h2chemistry@gmail.com. You can also join us on the Facebook page of the channel by the same name, that is H2O Chemistry. So see you again. Have a nice time. God bless you.